Alright, I'd like to continue the discussion of audio novelty functions and refine the ideas so that this will be ready for use as a pre-processing step for tempo estimation and beat tracking. So the observation that we made was if we're trying to pick up on rhythm, rhythmic events tend to look like vertical lines in a short-time Fourier transform magnitude plot. And that's because rhythmic events also often come along with very impulsive things like, claps. And we saw that these things are broadband, which means that they kind of occur over all frequencies. Now you could make a simpler thing that just looks for loudness, and that was an idea that came up in class, and you could probably make some progress with that, but it's not just loudness that matters. It's actually change in loudness, and really change in this broadband loudness. So we really do want to look for these vertical lines in these images. Okay. So the way we do that is by, this is a two-dimensional array. And what we can do is look and see, well, when does kind of an entire column of this array change a lot? So let me do this kind of using a loop first. So I'll say n is equal to sdb.shape1. So this is how many columns I have. And I want to compare a column to the column that comes directly after it. That means that I'm going to be able to do this for the first n-1 columns, and for the last one, well, there's no room, there's nothing that comes after it. So I will say that my nav function is equal to mp.zeros n-1. So I'm going to pre-allocate space to hold some kind of difference between columns. Okay, now I'm going to do this with a doubly nested loop here, just to show you, just to get you practice with 2D arrays and give you an idea. So what I want to do is I want to loop through every column. So I'll say for j in range n-1, right? So I want to go through all the columns that I can go through. And I also want to go through every row. So every row refers to a frequency index. And I'm looking to see how the amplitudes change at that row between two columns. So let me also say that n is equal to sdb.shape0. This is the number of rows. So how many rows I have. These are frequency indices. And the columns, these are time window indices. All right, but for each window, I actually want to go through each frequency index, right? I want to look and see over every frequency index, how do they change? So I'll have some accumulator variable. And what I'm going to do is loop through all the rows for this column, for I in range m. So this is a nested loop, a loop inside a loop. So the outer loop goes through the columns. The inner loop is going to go through all the rows for that particular column. And what I want to accumulate is, for now, let's say it's the absolute difference between the amplitude in the very next column and the amplitude in this column. So I would say the absolute value of this spectrogram at row I, column j. And actually I want to look at the next column. So I want to say row I, column j plus 1 minus what's at this column. All right? So I'll say the accumulator plus equals that. So I'm going to add that amount to the accumulator. And then when I'm done, I've accumulated the sums of the absolute differences over all frequency amplitudes. Let me save that result to my novelty function, and let's plot it. All right, so this, you notice that took a second. Let me spread this out a little bit, hang on. This will make my figure a little longer so I can see it, so I'll make it 8x4. Okay, so that took a second. I'm going to show you a way to do it much faster, but I wanted to write it out in its entirety so you really understood what this is doing. Okay, and so this is sort of what we arrived at in class and what I told you to get to on the assignment. And just to remind you, the units, let's actually get the proper units here on the x-axis. So every column corresponds to a window. The windows move along by hop length samples. So if I want to actually come up with the times for this, I have to say times is equal to np.arange n minus 1, but times the hop length over the sample rate. So every column moves by hop length samples. And if I want to convert that to units of time in seconds, I have to divide that by the sample rate. So I just wanted to get the units right because this will be important in a moment when we look at try to analyze tempo. So I'll say this is time elapsed, or seconds, time in seconds. Okay. All right. I mean, this is not terrible, but it's a little slower than it could be. But anyway, you can kind of see here. So this tune, I believe, was something like 83 beats per minute. So you see, okay. So you can kind of see the peaks are happening with the beat. Let me show you a slightly faster way to do this. So this first one is sort of I would call this the pure Python version. So version 1, the pure Python version with nested loops. Okay, let's see though if we can get away with just one loop. All right, so version 2, using a column slice to eliminate the inner loop. So we're going to have Numpy do some of the loops for us, and it'll be faster. Anything you can do in Numpy is faster because Numpy is actually backed by C and Fortran. It's compiled into much faster code. So let me start with the code I had here, but let me see if I can do something a little smarter for how I'm accumulating. So what I'll do is I can actually take out an entire column with a slice. So I can say that my first, or this column, SDB, column J plus 1, I could take out the entire slice. This is two-dimensional array slicing. So the colon here says take out the entire column, and now I'm going to specify which column it is. And I want to subtract the column I'm at, like that. All right. So that is almost there, but I want to accumulate the absolute differences there. So I actually want to say np.apps, and then I want to sum that up to accumulate. And now this is going to do the same thing that I did. Notice how much faster that was. I got the exact same plot. All right. So sometimes it's helpful as you're getting used to NumPy. Write it out in the pure Python way, like you're used to, like you learned in your Intro CS class. But then, if you can see an opportunity to use slices and these element-wise operations, so it's doing element-wise subtraction here, and go for that because it'll be a lot faster. Okay. Now there's something I could do to make this even faster. So version 3, eliminate all loops. How can we do that? All right. So here's where it gets a little fancy. So eliminate all loops with 2D slices and sums. Okay, so I'm going to start with this code again, and I am going to do the following. So I'm going to say diff equals SDB. So I'm going to slice out an entire column, but okay, so the first part of the difference is the next column. So what I'm going to say is start at index 1 and go to the end, minus SDB columns starting at index 0 up to the second to last element. So you might want to go back and review your slice notation, but this means, okay, take all the rows, but only take the column at index 1, so chop off the first column to the end. This one, take all the columns, take all the rows, but start at actually the first column and go up to the second to last one. Remember, this is 1 past where you end, and -1 is the last element. And so what this is going to do is this is going to element-wise, this is going to create a new array, which is everything shifted over 1 to the left. And I'm going to subtract from that the original one, but chopped off the last column. Okay, let me just actually, I want to plot this because it's kind of interesting before I finish this code here. So this is going to give us an image that will show us the things we're about to take the sum of. Hang on, let me plot this the same way I was doing up here. So, okay, hang on 1 second. All right. Okay, so what you can see in this image, and let me put a color bar here. This is actually, these are all the differences that we're computing from one column to the next. And you can kind of see, so if I compare it to this image, let me plot them side by side so you can see. So I'll do 2 of these plots. Okay, I think that gets me what I want. So let's look at these side by side. Let me throw a color bar on this one too. Okay, now they're lined up good. So if I look at this, so this was the original decibel short-time Fourier transform amplitudes. And this is the differences that I've been computing from a particular column to the next. And I can kind of see them here. I can see, you know, when it's not changing that much, I don't see a whole lot. But when it's changing, I can see these vertical lines. So this is getting closer to what I want. What I need to do, though, is first of all, I need to take the absolute value of this. So let me do that. So I can do that just by throwing an absolute value around the whole thing. That does element-wise. Okay. But I also need to sum these, right? And in particular, what I need to do is sum all of these along every column. So here's where we get super fancy. We can actually say, so let me make space. Let me make a plot for this. So I can replace this loop actually with, I can just say novelty function equals np.sum diff axis equals 0. What that's saying is sum down the 0th axis, which in this case is the frequencies. I want you to sum over all the frequencies. That's the first index of this array. And that's it. So you don't even need a loop. You can use all these element-wise operations. Now, of course, there is a loop happening somewhere on your computer when you run this, but it's happening in Numpy and it's much faster. So now let me show you that this comes up with the same result. Oh wait, hang on. Why did that end up 0? I meant to say nav fn. Okay, there we are. So that's the same thing. But this is like this is the ultimate way to do it. This is very, very quick. All right, so take a moment, let that sink in, and I want to then work on tweaking some of these ideas.